Hi, I'm Bob. Today let's learn quantile regression together. The standard linear regression is useful for summarizing the average relationship between the outcome variable y and the explanatory variable x, while the quantile regression provides us with information about the relationship between y and x at different points in the conditional distribution of the outcome variable. There were some attractive features of quantile regression. First, it's not as sensitive to the presence of outliers as OLS, so the quantile regression estimates are more robust. Second, the quantile regression model allows us to study the effect of the explanatory variable on the full distribution or any particular percentile of the distribution of the outcome variable. So it provides richer information of the data, not only the conditional mean. Open the dataset first, and then use the describe command to take a look at the information of the variables. The dependent variable is the total medical expenditure. The explanatory variables include an indicator for supplementary private insurance, the number of chronic problems, and 3 demographic variables, the age, and 2 indicators for female and white. We drop the observations with 0 expenditures and summarize the variables we will use in the model. In the first question, we run the quantile regression models using the total expenditure in levels as the dependent variable. We can use quantile regression, bootstrap quantile regression, and simultaneous quantile regression commands to do the estimation. In the basic quantile regression command, we specify the value of quantile. For the bootstrap quantile regression, we need to set seed and specify the number of bootstrap replications. The simultaneous quantile regression command can estimate coefficients at different quantiles. Finally, we run an OLS with robust standard errors. We store the results of each regression and then use the estimates table to compare the coefficient estimates and standard errors. For example, the estimated coefficient for the supplementary insurance is not significant in OLS, while it is significant in the median regression. The standard errors are much larger in OLS than in the quantile regressions. For the simultaneous quantile regression, we find that the estimates are very different at different quantiles. We can use the user-written command to draw graphs to show the coefficients over quantiles. For the second question, first, we show that the median of the total expenditure in levels equals the exponential of the median of the total expenditure in logs. Second, we show that if there's only one regressor, then the predicted total expenditure in levels is equal to the exponential of the predicted total expenditure in logs. This property holds not only for the median regression, but also for other quantiles, such as the 0.25th quantile. However, if there were more than one regressor, then this property no longer holds. For the third question, after the OLS regression, we use the post-estimation command to run a heteroscedasticity test. We reject the null hypothesis of constant variance and conclude that the error term is heteroscedastic. We can also see the pattern using the scatter command. The variance decreases with the number of chronic problems. Next, we use the simultaneous quantile regression command to test the hypothesis that the location and scale of the dependent variable medical expenditures varies with the number of chronic problems. We reject the null hypothesis that the coefficients are the same for the different quantiles. In the fourth question, we run the quantile regression using the basic quantile regression command and the bootstrap quantile regression command with different numbers of bootstrap replications. I could not find substantial differences between them. In the fifth question, we use a simulated dataset with heteroscedastic error term. The error term U is a function of x3 in this question. According to the scatter plots, for the positive part of x3, the variance of the error term U increases with x3. We run the simultaneous quantile regression and we find that the coefficients for x3 are quite different at different quantiles. And we can verify that the estimates are close to the theoretical values. Next, we vary the coefficient of x3 in the variance function and study its impact on the quantile regression estimates. We replace 0.5 with 5. And we find that the difference between the coefficient estimates at different quantiles becomes larger. Thank you very much for watching this video.